Roller coasters. I'm going to have a roller coaster that starts off up high, comes down low, does a loop-de-loop, comes back up high, but not as high as it started, and then goes down to the ground level. And I want to define a base height at the amusement park. Okay? And we can use that base height as our zero height if you like. So that's the ground of the amusement park. And I can go through and I can look at this roller coaster at different critical points to define some heights. And so the first critical point I'd like to define a height for is at the beginning. And that is 20.0 meters. The next critical point is going to be at the bottom of this first dip. And that's going to be at 3.00 meters. I'm just trying to provide myself with 3 sig figs here. At the top of the first loop, well, I'm going to come back to it actually. The top of the second hill, 15.0 meters. And then finally, we're going to finish it off at a height of 0 meters. Now this first loop, I'll tell you, it's not much of a riddle. But that first loop is going to be defined as being 2 meters lower than the second hill. Can anybody tell me how high the first loop is off the ground? 13 meters. 13 meters. Now these kinds of, these mind-bending riddles sometimes show up in textbooks, okay? So don't say like, oh, the gravitational potential energy is calculated with 2 meters. You have to work your way through these kinds of, these silly little problems, you know. So 13.0 meters. It's 2.00. Sorry, I'm sorry for my handwriting. Please forgive me. Excuse me if I stammer, it is just my grammar. If you like, I'll steal your bike and beat up on your grammar. Okay. Oh, it's a little it's a little poem that some kids in my grade 5 class made up.
What has my grandma ever done?
Okay. So I got this roller coaster up here. And I want to, I should say that there's some points here that I want to label with letters. This is point A. This is point B. This is point C. Point D. And point E. Just so we can have some specific positions that we can refer to later. Points A, B, C, D, and E.
What's the height for B?
Height for B is 3 meters, 3.00 meters. It's not a 5, it's a 3. Sorry, 3. Okay? 3 meters. All right, so first thing I want to do is find the total mechanical energy of the roller coaster. Now there's some information that hasn't been provided yet that's going to be absolutely essential to doing this, okay? So the mass of this coaster, I'm going to make it a nice round value. Mass of the coaster car is going to be 500.0 kilograms. What's another piece of information that I need to know if I want to know the total mechanical energy for the roller coaster? Keeping in mind, maybe you've forgotten, total mechanical energy is it's EG plus its EK at a given position on the roller coaster. What other piece of information do I need to know in order to find its total mechanical energy?
Velocity.
Yeah, velocity. Does it matter what point? Given how much information I know now, does it matter what point on the roller coaster I want to know velocity at? All right, I can give you velocity at? Yeah.
Will it just be the same E total at every point because the EG and EK change?
Yeah. E total will be the same the whole time. That's a good point. By what law? Yeah, law of conservation of energy. So according to the law of conservation of energy, the total mechanical energy is going to be the same at every point. Now, I sort of go through that in a little more detail with the grade 11s, but you guys just telling me off the cuff, you know that the total mechanical energy isn't going to change. And so assuming that this is a perfect roller coaster, and we could put that in brackets, no friction, no drag, no heat. Phew. This is a magical roller coaster in the land of physics, okay? So assuming that none of these things actually happen, I'm going to have total mechanical energy being the same from place to place. Assuming those things were there, though, and we're not going to do it right now, but assuming those things were there, I would have to start talking about percent efficiency. I could say, oh no, if this thing is 90% efficient, this roller coaster that is, that means I'm losing 10% of my energy over the course of the roller coaster. Now that would be one wild roller coaster. I mean, that would be a very greased up track. Because if you're 90% efficient, only losing 10% of your energy, frankly, I don't believe it at Wonderland. Okay? But if you were 90% efficient, what would your total, how would I calculate the total mechanical energy at the end? Yeah. Yeah, E total initial times 0.9 would be your total energy at the end. And let's say that I was going to claim that by this point, I'd only lost 5% of my energy. In other words, 95% efficient. How would I calculate it there? Yeah.
E total times 0.95.
Yeah, E total initial times 0.95. Now that's a really easy calculation to do, right? I'm not going to introduce it right now. But it is something that we could talk about. So E total at the beginning position, you tell me I still need to, or sorry, E total at any position. I can calculate EG at any of these positions given the values that I have at hand. I'm going to give you the velocity at the beginning. I'm going to call it velocity A. And what's a good velocity to start off at the top of the highest hill? 10 meters per second, don't lie. Let's 0.5. Let's make it 0.500 meters per second. Not quite stop. It's just getting over the top. Just. You don't want to start off going at 10 meters per second. You're going to be going at like 1,000,000 meters per second, but no, not 1,000,000, but a lot. You're going fast by the time you get to the end. Speed of light, bending reality. We're going to get a length contraction on our roller coaster. We're not going to do that. All right. EG. Let's rein it in. EG is mass times acceleration due to gravity times, I'm going to write h for height instead of delta dy from the baseline. I'm going to write h for height at position A. I'm being specific here. Plus 1/2 mass times velocity at position A squared. And so really, this is EGA and EKA. And assuming that there's no energy loss in this system, E total would remain the same. But let's be specific here. E total at position A. And we can start subbing in our values. I'm going to drop off the trailing zero so that I have some hope of actually getting all of my values in here. But the mass is going to be 500 kilograms times 9.81 meters per second squared times a height of 20 meters plus 1/2 times 500 kilograms times VA squared, which is going to be 0.5 meters per second, all squared. Don't forget to square the velocity. That's the most common thing that people mess up. Now I'm going to ask you guys to do this as two separate calculations. First find EG and then find EK. We'll write both values down and then we'll add them up. Okay, so we'll do it as two separate calculations. Has anybody got EG already? Sorry? 981? Is that right?
98,100.
Yeah, 98,100 sounds a little bit closer to me. I think there's a decimal place error there somewhere. 98,100 joules. E for effort. 500 times 20 times 9.81. The 500 times the 20 should get you quite a large number just on its own. All right. I think it'd be, what is it, 10,000 or something like that? Half times 500 times 0.5 squared. Yeah.
62.5 joules.
62.5 joules. Now this one's a really easy one to add up because you can see that there's two zeros here and 62.5, that's going to plug right in there nicely. We don't even have to do a calculator step there. We can say that the total mechanical energy at position A is 98,162.5 joules. Total mechanical energy. We can go somewhere else from there.